Hi, welcome back to Moose and Chemistry. This is VESPR Models Lesson 2. In today's lesson, we're going to look at a compound called Xeon Difluoride. All right, so let's go ahead and write that down. It's XeF2. All right, now, when we look at XeF2, the first thing we want to do is we want to find out how many electrons are we dealing with. First of all, please notice that this is a noble gas. Noble gases do not like to make compounds because they will be considered inert. But we can't force the issue. All right, so now let's look at Xe. Xe is in group 18, right? So it's going to have 8 valence electrons. And fluorine is in group 17. So it's going to have 7 valence electrons. So when we do the math, we get Xe, which would be 1 times 8 electrons. And we have 2 fluorines, so we say fluorine is 2 times 7 valence electrons. So let's go ahead and put this together here. And this is going to give me 8 electrons here, and this is going to give me 14 electrons here. Well, this will give me a total of 22 valence electrons. That's great. All right, now, so let's look at how we're going to proceed from here. So now we know that whatever structure we draw has to have 22 valence electrons. Let's look at some other things that we have to do. First of all, Xe, if you do the valence electrons, you notice that there are no docking ports. But we're going to have to open one up then, right? So our F is going to have this many valence electrons, which is 7. And it has 1 docking port, but it's going to be our wraparound atom. So we're going to have to take Xeon and open up a docking port. So that means these electrons right here are going to get moved around a whole bunch. So what we're going to do is, now that we know that we have 22 electrons to deal with, and now we know that we need to open up at least this unshared pair, for example, right here. Maybe that's the one we're going to open, or we can open up this one. So we need to look at this. So let me go ahead and erase this real quickly, and I know how many electrons I have. So let's go ahead and let's do our drawing. Okay, first of all, to recap, we have 22 electrons. Okay, and we need to know that we need to break apart in Xeon one of these unshared pair electrons, because our F, we have 2 of these guys that are going to be accepted into Xeon, which is a noble gas which doesn't like to bond. Okay, so now what are we going to do? Well, what we're going to do is this. We're going to put Xe to the center. We're going to put 1 F on the right, and we're going to put 1 F on the left. So the first thing we're going to do is we're going to connect these. So there's 2, there's 4. Now we have to make sure that we have an octet on our surrounding elements. So 2. And there's our 8 for that one. And here we go. So we got 2 in this dash there. 4, 6, and these dash will make 8. So this gives me 8 and 8 is 16. So we're still 6 electrons short. So what we're going to do is we're going to put 2 right here. So the extra electrons, they go to the core. And there you go. Now, the question is this the best possible shape? Well, we have to look at formal charge. Formal charge is valence electrons minus bonding electrons minus non-bonding electrons. Okay, so the formal charge for Xe comes in with 8 valence electrons, okay? And 2 of them, 1 and 2, are being bonded, so we have 8 minus 2. And then we have, of course, 2 here, 2 here, and 2 here. which gives me 6 non-bonding electrons. When we add that up, we get 0. So we know that that's a good start. Okay, so let me go ahead and erase those marks there. All right, now let's check out the formal charge of one of the Fs. We don't have to do both the Fs because they're the same. So fluorine comes in with 7 valence electrons minus 1 bonding electron minus 6 non-bonding electrons. So that also gives me 0. That's also good. So this is looking good. So our formal charge shows us that we did the correct structure. All right, now let's go ahead and erase this here. And we no longer need this, of course. And we no longer need the formal charge because we've already proven it to be the best possible structure. So now, what kind of shape is this? Well, let's look at this, okay? So what we got is we've got A for our core atom there. A, this is X, this is X. So this is AX2 at least, right? But look at this. This would be E1. This would be E2. And this would be E3. So this would make this an AX2 E3 shape. And what shape is that? That shape is called linear. Because if you look right here at AX2E3, the molecular shape is linear. Okay. Now, what about hybridization, hybrid orbitals? Well, we've been studying hybrid orbitals, so let's go ahead and look at this real quick. And pull this out here. Now, we're going to look at the hybrid orbitals for Xeon and the hybrid orbitals for Fluorine. Now, let's do the hybridization for Xeon first. Remember that a lone pair, like 2 dots, or a dash, which is called a sigma bond, they count towards hybrid orbitals. All right, so now, also it's important to remember that S can offer 1 dash, P can offer 3 dashes because it can hold 6 electrons, D can hold 5 dashes, and F, of course, can hold 7 dashes because it's capable of holding 14 electrons. All right, so let's clear that space up, and now we're going to look at the hybrid orbitals. The easiest way to do hybridization is not using an electron configuration method, but to actually count either unshared pair of electrons or sigma bonds. That's the easiest way to do it. So let's look at the hybridization of Xeon first. So what do we have here? We have 1 sigma bond, 2 sigma bonds, 3, 4, and 5 with the dots. So now S can hold 1, so there's your S. P can hold a max of 3 dashes, remember, so there's your 3. So this would be SP3. We put a 1 there just for right now. You really don't need to write that 1. But it'd be SP3. And then finally, we're going to look at, so that's 4. Okay? And we need just 1 more D. So our hybrid orbital for Xe is going to be SP3D. Pretty easy, huh? So that's the hybrid orbital for Xe. What about the hybrid orbital for fluorine? Well, fluorine has, of course, let's clean this up a little bit. Fluorine has 1 dash, right, between the Xe and the fluorine. So that's going to count as 1. And then these unshared pair, 2, 3, and of course 4, right? So now we have 1 for S and then 3 for P, because 1 plus 3 is 4. So that gives us the hybrid orbital now for E. See, this is not really that hard. And that's it, guys. Well, you be snarly, and we'll see you back here at Mucine Chemistry.